everybody, it's Mrs. Harbin. We're on our second to last unit, video notes 12.1. We're going to be talking about acids and bases. We have 1, 2, 3, 4, 5, 6, 7 things that we're going to get through in this video notes, and then we'll talk about them in class. So here we go. In the book, chapter 16 is your chapter. Foch says boxing hippo. Okay, please do this, really. All right, it's going to be easier to do after listening to this, but then try it. Okay, so acids. Acids have certain properties. The part of an acid that we look at that causes the properties of the acid is the H plus or H3O plus. They mean the same thing. That's what gets you. Okay, so that's a part of the acid that makes it acidic. They taste sour. They react with metals and marble chips, which are carbonates. They change blue litmus to red. So the way I remember that is litmus goes blue to red in acid. They have pH less than 7. You could also often find juices in foods. What about acids in everyday life? Well, muriatic acid kills molds on patios. I know that's probably something you know about. Okay, lemon juice is an everyday acid. Vinegar and battery acid are things that you probably have encountered. Okay, what about bases? OH minus is what gets you. So the part of a base that gets you is the hydroxide or OH minus. They taste bitter. You might have tasted it in unsweetened chocolate, olives, and of course when you eat those dandelions. What do bases do? They react with a lot of organic material by denaturing protein. Okay, so bases react with organic stuff. Oh, organic's awesome. Bases change red litmus paper to turn it blue. That's the opposite of acids. So red to blue, base for you, blue to red, acid. Bases feel slippery on your skin. They have a pH greater than 7. They're often used in cleaners. So bases in everyday life, Drano, milk of magnesia, and bleach and other cleaners are often basic. Okay, oh, look at that. I put that in blue. I put that in red because that's the color litmus turns. All right. So definitions of acids. After studying properties of things that were acidic, there were several definitions developed. Arrhenius' definition of acid is that when a substance is added to water, it increases the concentration of the H plus ions present. Okay, so HCl, when I put it into water, I get some H plus and I get some Cl minus, so the amount of H plus in that container goes up. All right, you could also write that as HCl plus H2O. And what you're going to get is H3O plus and Cl minus. So this and this mean the same thing. Okay, you really don't have an acid if it's not in water because that's what we define it as. So these two things mean the same thing. Okay, what about bases? Oh yeah, it's a base. An Arrhenius base is a substance that's, when it's added to water, increases the amount of hydroxide ions present. So when I put this in water, it dissociates or breaks apart into its ions, and you get sodium dissolved and hydroxide dissolved. And that was the same for here. These are aqueous because they're going into water. All right, just wanted to point that out. So I made this H red because I could show you this reaction in water, but it's going to look pretty much the same. You're going to get Na plus, all right, plus OH minus plus H2O, and you're like, but wait, that's the same thing. But I'm going to change colors here so you can see what I mean. I need a different color. All right, so here is my, let's see. Oh, I want that one to be red. All right, let me rewrite this. H-O, and then, oh, I did it again. This is why this takes so long. All right, red. All right, so H-O-H. So this H, so this is H2O, but this is not the same H2O that was before because this H on the OH is the one, this H2O came from the base, all right? And then you get some more H2O that came from that. So this turns into the OH minus. Okay, I know it's a little weird, but a lot of times with bases, we don't have to put in the water. Acids, you don't have to either, but it's a little easier to see. Okay, so there's another definition of acids and bases called the Bronsted-Lowry definition, and that's simply saying that acids are substances that give H plus. They're H plus givers. Bases are substances that are H plus takers. Okay, so if this is an acid, then it's going to give its H to that, and so we're going to get H3O plus because this HCl gave away its H plus, and then that turns into Cl minus. So if you look from here to here, the HCl gave away its H plus. So this is called an acid, and what it turns into is called a conjugate base. Okay. H2O. If you look what happens to it, H2O turns from water into H3O plus. So this is acting like a base, and this is called a conjugate acid. Okay. On the next slide, I'll give you the definitions. But in a Bronsted-Lowry definition, acids and bases work in teams. So NH3 is going to turn into NH4 plus, and H2O turns into OH minus. So if you look here to here, NH3 is a base. Why is it a base? Because what did it do? It took on an H and a plus. So that means its pair or its partner is called a conjugate acid. All right, H2O. If you look from here to here, H2O gives away an H plus. So H2O is a giver, H plus giver, because it turns into a conjugate base. This is the result of giving away H and a plus. Okay, now we have an acid and a base, and we're going to get an NH4 plus and a Cl minus. All right, so what does HCl do? HCl is an acid because going left to right, it gives away H and a plus, and it turns into what we call a conjugate base. NH3, if you go left to right, NH3 takes on an H and a plus, so it's a taker. Hey, you H plus taker, you're a base, and you turn into a conjugate acid. Okay. So, definition: a conjugate acid is what the base turns into when it gives away, what the base turns into by taking H plus. Okay. And so that's really an acid in reverse direction. A conjugate base is what the acid turns into by giving H plus. And it turns in, but it's really base in reverse. Base in reverse. So we'll keep looking at those reactions in class. All right, so naming acids, we did this before, but I'd use hydroic, itis, and it was icky. All right, so that's just a review. You should have that in your notes. I'm not going over it again. Okay, so examples. Hydroiodic acid, how do you know it's an acid? It says acid in the name. This is going to be HI because it's a -1 and +1. HCl is hydrochloric acid. All right, because it's chloride. And then I'd use hydro and ic. Okay, so all of those are examples of acids. All right, strong acids. There are 6 strong acids that you have to know. HCl, HI, H2SO4, HBr, HClO4, and HNO3. The only one you don't know the name of will be this one. This is perchloric acid. All right, PERCHLORIC, perchloric acid. So what makes these acids strong is that they ionize 100%, which means they dissociate completely. They break up into ions of H plus and whatever minus, no matter what. So the concentration of any strong acid is really the concentration of the H plus. So the molarity of the acid is the molarity of the hydrogen ion, because all of the acid turns into a hydrogen ion 100%. If you're looking at an acid and it's not one of those 6, then it's a weak acid. What do weak acids do? They ionize a lot less than 100%. In fact, usually less than 5%. So what that means is that they don't break up into ions totally, only some of them do. Strong acids, 100% ionization. Hey, how is that similar to bases? Strong bases. Groups 1 and 2, when they combine with hydroxide, they create strong bases. Okay, which means when you put those into water, you get 100% ions. So that means if I put 5 molar NaOH into water, I'm going to get 5 molar OH minus, 5 molar hydroxide, because all of this 5 molar NaOH breaks up into hydroxide ions. Now, if you have 2 hydroxides, you're really going to double your concentration of OHs. So, strong bases come from these 2 group hydroxides, but then the rest of the bases are weak. The most common weak base that you need to know is NH3, which is ammonia. It doesn't ionize completely, which makes it weak, but it's a base, even though it doesn't have OH in it. So, ammonia is a base. You say in your base voice so you don't forget. Okay, concentrated versus dilute. Concentrated acids or bases have a high molarity. Okay, 1 molar or higher is concentrated. Hey, guess what? You don't even have to have an acid or a base to have something concentrated. You just need a molarity. So I can have 1 molar CaBr2. Okay, That is concentrated because it's 1 molar or greater. It's not even an acid or a base. So you don't even know what it is to see if it's concentrated. You just need to know the molarity. Okay, less than 1 molar is going to be dilute. Okay, so dilute or concentrated has to do with the molarity of the acid or base. Dilute acids or bases have a low molarity. Less than 1 molar is dilute. Concentrated is 1 molar or higher. So molarity is the concentration. If there's a high molarity, it's concentrated, and low molarity, dilute. That is totally different than strength, because strength has to do with how much it ionizes. Okay, so be careful. Acid-base concentration is not equal to acid-base strength. 12 molar HCl is strong because HCl dissociates completely. And it's concentrated because 12 molar is a high concentration. 0.004 molar HCl is strong, which means it's HCl. It's a strong acid because it ionizes completely. But it's dilute because it doesn't have a lot of concentration. Okay, indicators are some things we use to tell the pH of an acid or a base. Litmus is really a weak acid. It's a complicated molecule, but it has an H+, which makes it an acid. Okay, so there's an equilibrium. So here's the equilibrium for litmus. Now let's use Le Chatelier's principle to work out what would happen if we add hydroxide ions. Okay, so if we add OH to this equilibrium, OH is going to meet up with the H+ and pull it out to make water. So H+ and OH- make water. What is that doing? It's pulling H's out of the equilibrium. So which way does the equilibrium shift? It shifts towards the blue side. So bases blue in litmus. All right. What if we add more H+? If we add more H+, we're adding more in, and we're going to shift the equilibrium to the left, and so acid turns lit red. Turns litmus red. Acids turn litmus red because you're adding more hydrogen, you're shifting the equilibrium, litmus is going to be red. Okay. Phenolphthalein is another indicator that's very similar, but different colors. Okay. What would happen to the equilibrium if we add acid? Well, acid means adding H+. If we add H+, we stress out this side and it's going to shift away. So phenolphthalein, isn't that a funny word, is clear in acid. Right. What if we add base? Well, base is adding hydroxide. Hydroxide reacts with H to pull it out and make water. Okay, if it's coming out of the equilibrium, then the equilibrium is going to shift. So phenolphthalein turns pink in base. Isn't that cool that we can use equilibrium to help us understand why indicators change color in acid and base? There are a ton of different indicators. Look at this range of indicators and their beautiful colors. So here's litmus. Here's that's not phenolphthalein. Here's phenolphthalein here. There's all these other indicators that'll help us decide if decide the pH. Okay. Anhydrides. Last thing we're going to talk about are anhydrides. Anhydride means without water. No water anhydride. So there are compounds that don't have water. For instance, CaO or BaO or MgO. They don't have water. And it's a metal with oxygen, metal oxide. So these are without water, they're anhydrides. Now these are called base anhydrides because when you react with water, they turn into, look at this, it turns into a base. If you react this with water, what are you going to get? Barium hydroxide. It turns into a base. If you react this with water, what are you going to get? Magnesium hydroxide. So it turns into a base. So metal oxides are called anhydrides. A metal oxide is an anhydride. What kind of anhydride? It's called a base anhydride, because when you put a metal oxide into water, it turns into a base. All right. So non-metal oxides. So let's throw some up here. HCO2. We'll say CO2, NO2. All right. So non-metal with oxygen. Non-metal with oxygen. Those are gases. All right. They are called anhydrides because they are without water. But they're called acid anhydrides. Why? Because when you react them with water, you get, in this one you get carbonic acid. In this one you get HNO3. You get nitric acid. So non-metal oxides, non-metal with oxygen, are called anhydrides without water, but they're called acid anhydrides because when you put them in water, they turn into acids. So acid anhydrides, these things, this pollution coming out of here is going into the air. And what's in the air? Water. So the water in the air reacts with the anhydrides and rains down acid rain. Oh, acid rain. Okay. So non-metal oxides are going to be gases. They're going to combine with water in the atmosphere and make acid rain. Metal oxides are going to be solids because it's an ionic compound. Those are going to be solids. And so they can't, they don't make acid rain because first of all they make bases. But then why can't we just use base anhydrides to fix acid rain? So these solids, we'd have to put them, we can't release solids into the atmosphere because they don't go up into the atmosphere. So we can't use them. Sorry, Charlie. So anyway, we're going to review. 2 ways we describe acids and bases. The Arrhenius definition and Broadside-Lowry. Hello, I'm an acid. Oh, you're a base. Oh, yeah. A base. Broadside-Lowry. Acids are H plus givers. Bases are H plus takers. H plus giver, H plus taker. Alright. Acids and bases have different properties. Make sure you write those down, get to know them. Anhydrides start without water. Okay, so they're oxides. But when you put them in water, they turn into acids or bases. Strong means they break into ions 100%. Weak means they stay together. Concentrated is lots and a little. Dilute is little and a lots. And equilibrium, indicators use equilibrium to tell us pH. Hey, Boxing Hippo says for sure, do that. Alright? You listen to this, so you should be able to do it. Just to check if you got anything out of this. Alright? Peace out. After you look at these objectives. Alright.